Welcome back, everyone. This is section number 3. Finally, we get partial derivatives, right? In section number 1, we did domains and ranges, and we talked about level curves and kind of just in general functions for multivariables. In section number 2, we did limits, which is kind of the beginning of calculus, and now we're talking about derivatives, which is kind of the second big topic in calculus. So in this case, we need to define these things called partial derivatives, and then we're going to state and verify Clairaut's theorem, which I'll show you what that is here in just a second. So, all right, the partial derivative of a function f with respect to x at a point ab, so this is a two-variable function here, is denoted f sub x, right? So we can't use this prime notation anymore. I would like to do just f prime, but I need to specify that this is an x derivative instead of like a y derivative, right? So later on you can see down here we're going to take a derivative with respect to y as well. So I need to be able to specify, is this an x derivative or is it a y derivative? And therefore we have to stay away from this kind of prime notation. I can't use f prime anymore because we'd have to wonder, is this an x or a y derivative? So this is given by, well, here we go. So this is the partial derivative with respect to x is going to be, and it's going to mirror very similarly, right, our limit definition for a derivative for just regular old derivatives back from Calc 1. So this is going to be f of a plus h comma b minus f of ab divided by h. So back from Calc 1, right, you didn't have these b coordinates, right? So you kind of, these wouldn't be here, but you would have something like this, f of a plus h minus f of a divided by h. That would be the derivative at a for the function f. Okay, so this is equivalent though. So this is the technical definition, right? And just like in Calc 1, we had the technical limit definition for the derivative, and then we learned kind of these tricks, right? These fast ways to take derivatives. And that's what I'd like to go over with you now, right? So this is equivalent to considering y a constant and just taking the derivative of x. So I want to find the partial derivative with respect to x for my function f. And here we go. So f sub x at xy. And if I just think of y as a constant, right? So x is my only variable, y might as well be 2 or 5 or something like that. So I would do 2x, and constants are along for the ride, right? There's that constant multiple rule. Okay, plus, okay, so here we have the derivative of sine would be cosine. Leave the inside alone, so that's according to the chain rule. Then we multiply by the derivative of the inside. And so imagine, again, this y might as well just be like 2 or something like this. So if I was to take the derivative of 2x, you would say, well, the derivative's 2, right? So I want to multiply by the derivative of the inside, and this is going to be equal to times y. Because again, y is constant in this case. So, right, I'm taking the derivative with respect to x, and it might as well just be 2, right? So if I asked you that, you'd say, well, the derivative of 2x is 2. So if I ask you what's the derivative of yx, well, it's y. So there's my final answer. You can see that these will be very quick. We won't have to use the limit definition, but it does take a little bit of practice. All right, next up, the partial derivative of f, derivative of f with respect to y at a point AB, again is denoted f with a little subscript here with y now, to say it's a y partial derivative at the point AB, and that's going to be given by, again, there's a very technical definition here. This is the limit as h goes to 0, and now we have the h's are in the y coordinate. So it's going to be a comma b plus h minus f of ab divided by h. And again, there's a fast way to do these things. It's equivalent to just considering x a constant and taking the derivative of y. So here I have this same function, but now I'd like to figure out the y partial derivative for this function. So if I was to take the derivative here with respect to y, remember x squared is a constant. It might as well just be 2 squared, aka 4, right? And so when you take the derivative of y, well, you just get the constant. So in this case, x squared. Plus, well, the derivative of sine is cosine. Leave that inside alone. Then multiply by the derivative of the inside. So again, I'm taking a derivative with respect to y. So x might as well be a constant. It's like 2 or something like this. So if I take the derivative of 2y, you would say that the derivative is 2, right? So if I take the derivative of xy, you should say that the derivative is x, right? Because again, we're treating x like a constant, y is the variable when you're taking the y partial derivative. And there's my final answer. Again, this takes a little bit of practice, but it's very fast once you get the hang of it. All right, there are also some other notations out there, right? Kind of like the Leibniz notations back from Calc 1 days. So instead of just this f with the subscript, right? Sometimes you shorthand this and you just say f sub x, right? So this is the partial derivative of f with respect to x. But again, we're not specifying the x and the y there. This can also be denoted the partial derivative of f with respect to x, or the partial with respect to x of f, right, of xy. Also, f's quite often are denoted with z's, right? So z is equal to a function in x's and y's. So you may use something like this. And then finally, you may see d sub x of f. And this is a little bit more technical notation that you're likely to see in kind of higher level math courses. All right, so if you like first derivatives, the claim is we can also define second derivatives, right? And this should be twice as much fun. Okay, let's go ahead and do that really quick. And the claim is, well, these things actually do have uses. So if I wanted to go ahead and specify a second partial derivatives, of f. Well, here are some ways that these things are denoted. So, for instance, the second partial derivative, both of them with respect to x. So you take the partial derivative with respect to x, and then you do it again. This is often denoted f sub xx, right? So that you're taking two partial derivatives, both with respect to x. Here are some other notations. If you take them both with respect to y, again, other notations. And then finally, these mixed partials. These ones are interesting. So first you take a derivative with respect to x, then you take a derivative with respect to y. So this is denoted xy here. So first x, then y. But notice, if you use the Leibniz notation here, kind of this is almost like a composition notation. So you work inside out. So here the x is on the right-hand side, and the y is on the left-hand side. That's kind of opposite of what we have over here. So again, kind of you have to be careful about the notation. So I make a note down here. With the subscript notation, we read left to right to get the order of differentiation. In these partial notations, so this one over here, we read right to left to get the order of differentiation. And so again, this is modeled here when you first take a derivative with respect to y and then x, right? So here with the subscript notation, you would use yx to say first y, then x. But over here, if you're using the partial notation, you say first y, then x, right? You read in the opposite order, right to left, instead of left to right. Okay, however, the claim is this doesn't make so much of a difference thanks to Clairaut's theorem. So the claim is if these second order mixed partials, right? So f sub xy, so if we take the derivative first with respect to x, then with respect to y, and f sub yx, again, now we're taking the derivative with respect to y first, then x, are continuous and defined around the point AB, then f sub xy at AB will be equal to f sub yx at AB. So if you confuse the order on these things, right, if you switch the order, if you do first y then x, it'll be the same thing as first x then y. So let's go ahead and check this, right? So I have a function here, so xy plus x sine y plus y over x. And in the first case, I would like to differentiate with respect to y first, then x. And here I'd like to differentiate with respect to x first, then y. So let me, I want to recommend you pause the video and try to do this yourself, right? Get as far as you can, and then I'll explain the answers here in just 1 second. So go ahead, pause the video, and then try to get as far as you can, and we'll come back here in just a second. All right, so this is what I have so far. I haven't evaluated out it entirely yet, but I did the first partial derivative, so in this case with respect to y. So, okay, when I took the derivative of xy with respect to y, well, the y goes away, and then you just have x. Here, again, I'm taking a derivative with respect to y. This x is a constant. It's along for the ride. So the derivative of sine is cosine. And again, I'm taking a derivative with respect to y. So that just stays in sine. And then finally, well, the derivative of y over x, again, with respect to y. So this might as well be like y over 5. So if you take the derivative of y over 5, you're going to get 1/5. If you take the derivative of y over x, you're going to get 1 over x. So again, thinking of x as a constant when you're taking a y derivative. Likewise down here, so here I'm taking the derivative with respect to x first. So when I do that, here the y is along for the ride. Y is constant, so the derivative of x times y will be y in this case. Here, x times sine y, well, again, I'm taking derivative with respect to x. This might as well be sine of 5, or sine of pi, or sine of 0, or something like this, right? It's constant. So when I take the derivative of x times a constant, this might as well be 5. You're going to get 5. Well, in that case, our constant is sine of y. And then finally, y is constant. It might as well be something like 2 or 3 or 5 or whatever, right? And then I have this, well, this is technically like x to the negative first power. So when you take the derivative of that using the power rule, that negative 1 comes down, and then you get x raised to the negative second power. So that's why I have x squared here. Notice if you were to compare at this point, they don't look the same, right? So if you take the wrong first derivatives, right, you get completely different answers. However, now let's go ahead and do the second derivative of each one of these things. So now the outside one is that I'm taking a derivative with respect to x. So let's go ahead and apply that. So when I do it here, I take a derivative with respect to x, I get 1. Again, taking the derivative with respect to x, I would get 1. This is constant. It's along for the ride. And then if I take the derivative of x here, well, this is technically, right, x to the negative first. So the negative 1 would come down, and then I'd have raised to the negative second power. So that's going to be the same thing as 1 over x squared. So, okay, that's my final answer for part A. For part B, if I go ahead and I take the second derivative right here, now I'm doing it with respect to y. So if I take the derivative of y, I get 1, right, because the coefficient in front of this is 1. If I take the derivative of sine, I get cosine of y. And then if I take the derivative here, again, this x is a constant. It's along for the ride. So this all stays the same, and the derivative of y, again, I'm taking a derivative with respect to y here, is 1. So we can notice that our answer from part A is the same as our answer from part B, right? So if you change the order in these partial derivatives, thanks to Clairaut's theorem right here, it's saying that you'll get the same answer. All right, so that is the end of this video. We will go over some more details, some applications and whatnot in class. I'll see you guys then.